Now let us look into polynomial interpolation. So the definition is interpolation is a process of estimating values between known data points and approximating complicated function by simple polynomials. So why do we need an interpolating polynomial? Let us say we are given values of the function f of x at different points x0 to xn. Now we want to find approximate value of the function f of x for a new x that lie between these points. So let f of xi is equal to fi for I 0 to n. To find the value of f at some new point x is quite impossible, as f might be unknown to us, or even if we know f, it might be very difficult to compute f at x. So we want to replace f by some function g quite close to f, and g is very much a simple function. So the standard idea in interpolation theory is to replace a general function f by a polynomial function p, and this function p is called the interpolating polynomial. Now, if we have n plus 1 distinct points and let f of xi is equal to fi for I 0 to n, then the problem of polynomial interpolation is to find a polynomial p n x of degree less than equal to n, such that p of xi is equal to f of xi is equal to fi for all I from 0 to n. So what exactly is the fundamental principle behind polynomial interpolation? Now it can be known by the Weierstrass approximation theorem, which says that suppose that f is defined and continuous on any interval, let's say a to b, for any epsilon greater than 0, there exists a polynomial px with the property that f of x minus p of x is less than epsilon for all x in the interval ab. So we can basically have a polynomial p of x that will approximate our given polynomial f of x with as much good accuracy as we want. An important remark here is that let us say we have two distinct points. We can always pass a straight line through that is a polynomial of degree 1. Now if we have three distinct points, we can either pass a parabola, a polynomial of degree 2, or a straight line if all the 3 points lie on the line. So in general, if we have n plus 1 distinct points, a polynomial of degree of at most n can be fitted. So from this remark, we come to a theorem of existence and uniqueness of polynomial interpolation, which says that given n plus 1 distinct points x0 to xn and n plus 1 values y0 to yn, there is a polynomial px of degree less than equal to n such that p of xi is equal to yi for I from 0 to n. The polynomial p of x is unique and among the set of all polynomial of degree of at most n. Now, let us look into what exactly is error in interpolating polynomial. So, let us say we have n plus 1 data points and let x be any point belonging to the domain of the given function f. Now, we assume that f is n plus 1th time differentiable, where ix is the smallest interval containing the nodes x0 to xn and x. So, ix is basically the domain of the function f of x. So, at any given point, the difference between the function and the polynomial is given by f of x minus pnx, which can be computed by the formula, this formula. So there are four methods to calculate this interpolating polynomial. We will discuss them one by one. At first, we will be discussing Newton's forward and backward interpolation formula. So let us say we have got tabular points x0, x1 to xn, and these are equally spaced. So we need to know about certain difference operator. The first is the shift operator called e. Now it says that e of f of xi is equal to f of xi plus h. So which basically means that um, when we operate e on f of xi, it gives the function value at the next data point, that is xi plus h. Similarly, we have forward difference operator denoted by delta. Delta f of xi is equal to the value of the function at a forward point minus the present value. Then we have the backward difference operator nebula, which says the value at the present point minus the previous point. Similarly, we have central difference operator as well. These three are the important ones. And similarly, we have other important results as well, which needs to be kept in mind. Similarly, we have higher order differences as well. What we discussed now was the first order differences. Now, for both forward and backward, you can pause the video and look into its derivation and remember the results. This is for the backward. Now, let us look into forward difference table. So, these are our data points and these are the value of the function at those data points. This is the first order forward difference, this is the second order forward difference, this is the third order forward difference. Now, in order to calculate the forward difference, all we have to do is subtract the data points. So when we subtract f1 minus f0, we get delta f0. When we subtract f2 minus f1, we get delta f1. And when we do f3 minus f2, we get delta f2. Similarly, when we subtract delta f1 minus f0, we get delta 2 f0. So, and similarly, when we subtract delta 2 f1 minus delta 2 f0, we get the third difference. And an important thing to note here is that when we are using the forward difference formula, we have to use these values. And this is the backward difference table, which is quite similar to the forward difference table. So all we have to do is f1 minus f0 to get the backward delta f1. And important thing to note here is that when we are using the backward difference formula, we have to use these values. So let's look into the Newton's forward difference formula. So this is for the case of linear interpolation when we have two data points, x0 and x1. And this is the formula, and the value delta f0 we can find by the forward difference table. Then we have the quadratic interpolation formula, and we can get these values from the forward difference table. We have three data points here, x0, x1 and x2. So this is the generalized formula for Newton's forward difference formula based on n plus 1 data points, and we can get these values from the forward difference table. And this is a generalized formula for Newton's backward difference formula, where we can get these values from the backward difference table.